Right. Hello everyone, this is another supplemental video for our BIS103 lecture 3 on glycolysis. And in this video, what I want to go into is some of the definitions and understanding of cofactors and introduce us to the first one that is really important for glycolysis. So what are cofactors? There are actually different kinds. We can have metals, for example. These can be bound to enzymes and can be important for catalysis of the enzyme, or they can be bound to enzymes and actually provide structural support, can be important in enzyme folding, substrate binding, and so forth. And our second group here are coenzymes. These are now organic compounds. They usually have a catalytic function, less a structurally function. And what is important to note here is that they can be either covalently bound to the enzyme or transiently bound. The difference here being that covalently means the coenzyme is permanently bound to the enzyme, whereas if it is transiently, the coenzyme can actually bind to the enzyme and be released as part of the catalytic function of this enzyme. So we can differentiate the two, and we'll see a few examples for either throughout the quarter. So keep in mind, actually both these metals as well as coenzymes would fall under the definition of cofactors, but metals are not coenzymes. So you have to have an organic compound for it to be defined as a coenzyme. For the coenzymes, another important aspect that these can be altered during the reaction. So they themselves can change. And sort of one of the examples that we will use today for glycolysis is our NAD or NADH. So this can exist in an oxidized or reduced state during catalysis. And I'll go into more detail just in a minute. And what is important in this context of these coenzymes being able to change during a reaction is that we have to have a mechanism to regenerate them, right? If you're only doing the one reaction of reducing NAD to NADH, you're running out of the oxidized form. That obviously would be a problem for metabolism if you're running out one component. So we must have this mechanism for regeneration, and that's what we call cofactor balance. This term cofactor balance will follow us throughout the entire quarter and is really a crucial aspect of maintaining metabolism and sustaining life through biochemistry. Right? There are a number of cofactors. Sadly, most of those we cannot synthesize. Humans cannot synthesize them. Among those fall all our B vitamins, right? So I listed the relevant B vitamins just down here. We'll actually be acquainted with all of them throughout the quarter, and I'll touch base on the individual ones when we get there. But these are really critical. They're essential for us to get those, or at least parts of these compounds, through our diet. The one I want to introduce you to today for glycolysis, this is the one we'll be using during glycolysis, is NAD or NADP. Right? I've mentioned this acronym a number of times now already in lecture 2. This is actually what it looks like. It's nicotinamide adenine dinucleotide. And we'll see that in some organisms, some pathways, it actually will be used in form of a phosphorylated molecule. But for the most part, we'll actually be looking at NAD here, nicotinamide adenine dinucleotide. Structurally, it actually should remind you of something, right? If you look at this backbone here, you have an adenine, you have a ribose here, so our pentose sugar. You have two phosphoryl groups, one phosphoester group, and then a phosphoanhydride group here. And then you have another sugar, and then the functional group of NAD. Right? If you look at this molecule here, if you would just replace the sugar and this group here with another phosphoryl group, you would have ATP. Right? So the backbone structure of ATP and NAD is actually very, very similar. Okay? The business end, so the functional group of the molecules is different now. What is key here is this group that I highlighted in pink, right? And that's called niacin or vitamin B3. And this is actually where the action in NAD happens, right? This group here can exist in either an oxidized or reduced state, right? You see it here with a double bond in the ring, or you can reduce this to remove this double bond, and you actually have another hydride coming in here. The bioactivity of this compound will change. Right? Now niacin, now this functional group, right? We can get through our food. Some compounds, as we can get it through, is for example nicotinamide or nicotinic acid. These are some forms on how we can get this, but it will be essential. Here's a sort of zoomed in to the business end of NAD now. Right here, the rest would now be the entire backbone of the structure. I'm just showing the functional group. And again, we can see here, this is the oxidized form with a double bond in the ring. This now can be reduced and it can accept electrons as well as two hydrides, right? And so the electrons are used to reduce this double bond here, and we're taking on one of the hydrides up here to change the molecule, and one of the hydrides actually in this particular case will stay in solution. This mechanism is exactly the same regardless of whether you look at NAD or NADP, right? And so in its oxidized form, we call it NAD plus or NADP plus. In its reduced form, we call it NADH or NADPH. So this is really important, and you want to remember NAD throughout the quarter. We will use it over and over again for a multitude of reactions. This is what it actually looks like in a protein, just to give you sort of a sense of perspective. This is an NAD-dependent dehydrogenase, right? So here's a protein just sort of shown in a cartoon, and inside here in the active site bound, we have our NAD molecule, just to sort of give you an idea of the size of this within a protein. What it does now in these enzymes that are NAD-dependent dehydrogenases is that it helps with the oxidation and reduction reactions, right? It's actually functioning as an agent here. So you could imagine you have one of these dehydrogenases, you have a substrate coming in here that's a reducing agent. We call it AH2 in this case. We want to oxidize this. And so during the enzyme catalysis now, NAD plus in its oxidized form will get reduced, so acts as an oxidizing agent, will now have the oxidized product. So the electrons and the hydrides have been moved from the substrate to NAD plus. The substrate gets oxidized to A, and NAD plus gets reduced to NADH and H plus. Right? So it's really critical here to facilitate this reaction. We need our cofactor NAD plus in this case. Okay. And right, as we said before, this is one of the examples where our cofactor is altered during the reaction. So it is critically important that we regenerate NAD plus. Otherwise, right, this reaction cannot occur anymore if you're running out of NAD plus. What is important to note is that this doesn't have to happen in this particular reaction. It can happen in another enzyme reaction and you get NAD plus through that. It can even happen in another pathway. And again, we'll see examples of that. Just for a little bit of history, why NAD is so important, and sort of to highlight that for you, actually the deficiency in niacin, so right, in our vitamin B3, the business end of our NAD, can actually cause diseases, and one of them is pellagra. And so what is important to note is here that we can synthesize niacin from tryptophan, from our amino acid, but it's extremely inefficient. So humans really rely on getting niacin through their food or to get enough of tryptophan to overcome the inefficiency of the reaction to produce enough niacin de novo. Okay. One of the issues now is that many of our staple foods, for example, corn or sorghum, are very low in tryptophan. So what can happen here actually is that if you rely on these staple foods almost exclusively, that you can have a deficiency in niacin and you can have a multitude of symptoms, starting some sort of mild dermatitis, and progressively as you are getting an increased deficiency in niacin, it can move all the way to dementia, and you can eventually even die of it if you do not get enough niacin or tryptophan through your food. I should note that there actually have been a number of recent outbreaks of pellagra, so it's not a disease of the past, especially in refugee camps, countries that have a shortage of food. Pellagra actually has been coming up frequently over the past years. Interestingly, actually, the person who actually found out that it's a metabolic deficiency was Joseph Goldberger, because initially, because of these symptoms of dementia, people were thinking that it's actually a mental disease. Potentially, it could be infectious. People didn't really understand that it was a deficiency in metabolite. And what Joseph Goldberger did is he observed that in these hospitals for pellagra, the patients would get progressively worse, while the staff who was taking care of the patients, nurses and so forth, were fine. The difference was in the food they were provided with. The patients were getting much less nutritious food than the nurses would get at this time. And so he observed this and simply started to switch the diet for the patients and saw that they were getting quickly better, and deducted then that it must be part of the food that actually is causing this and that it's not a mental or an infectious disease. So it was simple scientific observation here that really caused Joseph Goldberger to further investigate this and understand what the mechanism of pellagra actually is. Right. I'll end here. This is just a short overview of cofactors, again, accompanied with our lecture 3 on glycolysis. So you can watch these alongside to improve your understanding of what's happening in this really important pathway.